I would say the most important skill in Python, especially if you're dealing with data, if you're in science, if you're in engineering, if you're in mathematics, if you're in anything, is learning to properly use the NumPy array. Now, there's lots of NumPy tutorials out there that talk about the different functions. I have one on this channel as well. You can check that out. But nobody really focuses on the power of manipulating NumPy arrays on their own to do operations that might help with practical examples. This is the purpose of this video. I'm going to show you the functionality that you might not be aware of if you've never seen before, that I guarantee will boost your productivity working in Python and boost the speed at which your code runs by a significant factor. So the main library you're going to use in Python for almost all numerical operations is going to be NumPy. Doesn't matter what field you're in. I mean, you might use pandas sometimes to open data. You might use other libraries, but really the foundation of most of these libraries is NumPy arrays. And so you can define an array like this. You have x is equal to all these values here. And it's very easy to index x. So there's x itself. I can take the first element of it, the second element, etc. You probably already know this. This isn't why you're here at the video. It's easy to do operations on NumPy arrays. The reason why they're so nice is that when you apply an operation to it, like x squared or sine x or e to the x, it does that operation on all the elements of the array at the same time. So it will do 1 squared, 4 squared, 6 squared, 7 squared in this. Same with sine x and e to the x. So it will just apply this operation to all these elements in the array and return an array of the same size. That's what makes NumPy so nice. And that's the functionality of it that sort of all these more advanced features builds upon. It's easy to create what I call base arrays in NumPy. So for example, if you want an array that consists of 10 zeros, for example, it's easy to make with the np.zeros function. And I can look at those values here. If I only want 5 zeros, of course, I can do something like that. There's also the np.ones function to fill it with ones. And now, for example, suppose I wanted an array filled with 5s. Well, if I have zeros and ones, I can do that very easily. I can create, for example, an array of 10 ones, divide them by 2. It will divide every element by 2, and I'll get an array of 10 values of 0.5, which you can see here. The other nice thing, especially for plotting functions, is that you can create an ascending array of values. For example, this goes from 0 to 10, and I have 100 values. So if I look at this array, it creates sort of a linearly spaced, that's what linspace means, from 0 to 10, 100 different values. There's also the arrange function, so rather than specifying how many there are, you specify the step size. It will give me an array from 0 to 10 in step size of 0.01. And then, of course, the nice thing about that is that I can plot functions like that. So I have x, for example, so from 0 to 10 in steps of 0.01, and x squared, and it'll plot all those points on the plot, and I'll get a really nice looking plot like this. This is just a function x squared. So the real purpose of this video is going to be multi-dimensional arrays. You build on this functionality of the, single dimensional arrays, and you can use that to do very powerful things with multi-dimensional arrays. So for example, here I'm creating a base array of ones, and rather than just saying 10, which gives me a one-dimensional array of 10 ones, I can create a 10 by 10 array like this. So this is a two-dimensional array where each element of the array is itself an array. So for example, if I take the first element of this array, x0, it gives me 10 ones. Same thing with x1, x2, x3, x4, all the way up to x9. So there are 10 different arrays within this array. Now, multi-dimensional arrays get complicated, and you might want to see what they look like, for example, but it usually takes up a lot of space, especially if they're, 5-dimensional, 6-dimensional arrays, which you deal with in things like machine learning all the time. And so the way to get around that, and this is the number one function you should be using all the time, especially if you're coding in a notebook environment. You get a new array. For example, this array here, x is np.ones 10, 10. So I have a 10 by 10 array, whatever. Maybe you don't know what the shape is. Maybe you load some array for whatever reason. You should always be, whenever you load a new object that you know is a NumPy array, use the .shape attribute of the array. It's going to save you so many headaches. When you're dealing with this, you'll see that later in this video as well. So for example, suppose I get x and I don't quite know what it is. Well, the first thing I'm always going to do is I'm going to go x.shape. And I say, okay, well, the array is 10 by 10. So it gives you an idea of the dimensionality of the array. So for example, I know if I take elements like 0, it will give me a one-dimensional array. So using this sort of notation here, you can create arrays of arbitrarily strange dimension. So for example, this array, which you probably wouldn't see in practice, is a 3 by 5 by 2 by 5 by 3 by 1 array. It's a 6-dimensional array. For example, this is a complicated array. Maybe you would load something like this. So I have X that looks like this. And maybe you load it and you see this and you think, what the heck am I looking at by displaying it like that? Well, always use the shape attribute, right? So you see that I have an array like this. Well, I know that there's 3 arrays stored in that with this shape. And each of these shapes, I know that there's 5 arrays of that stored with this shape, and so on and so forth. So for example, multi-dimensional arrays come up in applications all the time. So you might think this is very abstract. Well, maybe not. Maybe there's 3 houses. Each house has 5 rooms. Each room has 2 couches. Each couch has 5 pillows. Each pillow has 3 stains. And each stain has 1 attribute to it. Maybe this would be 2. So each pillow has 2. Each of those stains is, has 2 different quantities or qualities to it. So that's just off the top of my head, but this is how you would index it, something like that. So suppose there's 3 houses, each house has 5 rooms, each room has 2 couches. Suppose I wanted the first couch of all those houses of all those 5 rooms, right? Well, I would index it like this. So this is the couch dimension. There's 2 couches in each of these 3 houses with 5 rooms with 2 couches. So I would index like this. I would say, okay, I still want to know all the houses. I still want all the rooms in each house, but for all those things I'm looking at, I only want the first couch in each room. Well, I would index that like this, for example. And you still get some weird array, but again, if I look at the shape, it looks like this. So in this example, there were 3 houses. Each house had 5 rooms. Each room had 2 couches. Each couch had 5 pillows. Each pillow had 3 stains. Each stain had 2 attributes. Now, because I've only taken the first couch in those rooms for all those different things, now there's 3 houses. Each house has 5 rooms, and I'm looking at the first couch, right? And then there's 5 pillows on that first couch, 3, 1. So I'm removing one of the dimensions. That's sort of what the multi-indexing looks like. So this dimensionality comes when you're dealing with objects that have sort of properties to them, and those properties have properties, and those properties have properties, right? You'll see that with image arrays, which we'll get into now. So in machine learning, you often deal with 5-dimensional arrays. I deal with this all the time. Well, they're not quite NumPy arrays, but they're basically the same thing. They have the same functionality. So for example, maybe I have 10 3D MRI images. An MRI is a 3D image, right? You know the value at every voxel in the body. 3 feature maps each. And the width and height is both 256. So it's 256 by 256 in each sort of slice like this. And there's 100 different slices. So that's like a 3D image, for example. So this would be my shape like that. So there's 10 different images. Each image has 3. Well, in normal images, those would be color channels, red, green, and blue. In MRI, it's a little more complicated. But you can imagine that each pixel, rather than having a single value in an image, it has 3 values, like a colored image. And in MRI, those values correspond to different things. And then you have the 3D array type. So then you have this complicated thing that you might load in that looks like this. And you're given this data and you think, oh, what am I going to do with it? Always check the shape. And that gives you that intuition. It says, okay, I'm loading something where there's 10 of something. Each of those 10 things has 3 things. Each of those 3 things is 256 by 256 by 100, which is like a 3D box. So 10 images. Each of the pixels has 3 different values, and there's 256 by 256 by 100 different pixels or voxels in this. And so I said there's 3 feature maps each. Maybe suppose those are red, green, and blue. So that's not the case in an MRI, but suppose these 3 color channels correspond to red, green, and blue. If you want the 3rd feature map, maybe that's the green color channel in this image of the second image. You could index like this. You could say, all right, well, there's 10 images. I'm going to take the second image. That's index 1 here. Let me just erase this and go through it. So the first index is 1 because 1 corresponds to the second image. 0 corresponds to the first image. And the 3rd feature map would be the final index here. So I could do -1, which gives me the final index there. And I look at that array, and I get something complicated. But if I look at the shape, it tells me, well, now I'm extracting a 3D array. I have one of these 3D images, one of the color channels of that image, and I should be getting a 3D array. Suppose you then want the 95th slice. So there's that 3D array, which has a slice here, 256 by 256, 256 by 256, 256 by 256 in the planes, and I want the 95th slice. Well, I can index the same thing here. So this is also the same as 1, 2.shape because it's the 3rd feature map. So I get the second image, I get the third feature map. I still want all 256 by 256 pixels, so I'm not selecting those. In order to keep all of those, I use this notation, the colon, so I don't want to choose a specific value of those. And then for the slice index, I would choose 94, right? And then again, I get an array that looks like this. You could tell it's a 2D array. And if I want to make sure that I indexed everything and I get the right shape, I can call .shape. And again, I'm getting a 256 by 256. That's what's known as an axial cross section of somebody in a 3D image. So if you have an array of a specific shape, you can also reshape it to a specific dimension. So for example, suppose I have an array here. It just goes from 0 to 19 in steps of 1. And maybe I want to reshape this array to some other dimensionality. Well, as long as the dimensionality divides 20, right? 20 things total, I can do that. So for example, a 2 by 5 by 2 array has 20 elements total, right? 2 times 5 times 2. That's the number of elements in this dimensionality. So I can create this result array like this, and I get something that looks like this. And if, again, it looks kind of complicated, if I look at the shape, it's 2 by 5 by 2. That's the dimensionality. There's 2 things. Each of those 2 things has 5 properties. Each of those 5 properties has 2 properties of its own. That's dimensionality, right? And you can note the order which they're filled, right? Because you might think, well, how does this fill these elements? In what particular order does it do it? Well, if I take result 0, you can see it looks sort of complicated like this. But it fills it so that I have 3 dimensions, right? First dimension, second dimension, third dimension. The first element is going to be 0. The next element is 1, and then there's only that many things here, right? The last dimension is only 2, so then I have to go to the second dimension. So 1, 0. That gives me 2. Then I index up 1, 1, 3, 2, 0. That gives me 4. So it indexes like that. So it's always the last dimension that gets filled with the 0, and then 1, and then 2, and then 3. So think about the ordering of that. So that's how you would reshape an array once you get it. And there are reasons for that, and we'll get into examples where using this reshape functionality is very useful. This is probably the most important thing about NumPy, the broadcasting rules. So when can you multiply 2 arrays together? Well, if they're both one-dimensional, you can multiply 2 arrays together if they're the same size, obviously, right? And then each element gets consecutively multiplied. And I'll read this over really quick, but the examples make so much more sense. To determine if they're compatible, you start with the rightmost dimension, you work your way left. 2 dimensions are compatible if they are equal or one of them is 1. And that might seem complicated. You could read this, but the examples make a lot of sense when you go through them and you realize that we're following these rules. So for example, here's 2 arrays, A and B. A has dimensionality 8 by 1 by 6 by 1, and B has dimensionality 1 by 4 by 1 by 1. And we want to see if it's possible to multiply these 2 arrays together. Well, we start with the rightmost dimension, so here, and they're compatible if they are equal. So in this case, they're equal, so they're compatible. Then we move our way left, and you have 6 and 1. And you ask, well, are these compatible for multiplication? Well, they're not equal, but one of them is equal to 1. So they are compatible for multiplication. And the reason for that is because this particular dimension only has 1 element. So you can broadcast that to all 6 elements that would be in this array. And so they're compatible if one of them is equal to 1 because you have that broadcasting occurring. The next dimension, 4 and 1. Well, they're not equal, but one of them is equal to 1, so they're compatible. 8 and 1, well, they're not equal, but one of them is equal to 1, this one, so these are compatible. So if I define these and I multiply them together, I can do that because these arrays are compatible. If I were to change this, for example, to 2 by 4 by 1 by 1, well, these 3 dimensions are compatible, but 8 and 2 are not equal, and one of them is not equal to 1. So if I try to multiply these arrays together, it's going to throw me an error. The reason for that is because it can't broadcast this 2 into these 8 elements. If there's only 1 element, it can just copy that output and multiply each of those 8 elements because it's, well defined. But if it's 2, it doesn't know which of these to choose. And so that's why it's defined such that you can multiply them if the dimensions are equal, in which case it does each of those elements consecutively. For example, np.array 2, 3, 4. Let me fix that. 2, 4. And I can multiply it by this, 2, 3, 5. These have the same shape, So we'll just do 2 times 2, 3 times 3, 4 times 5. But if these have different shapes, it doesn't know, like it can't do element wise, and it can't do component wise because these aren't the same size. But if I do just a single element, in other words, one of the dimensions is 1, it can do that. So that's sort of the rule of NumPy. This is the generalized case of that with dimensions. Also, if two arrays aren't the same size, the smaller one is assumed to be filled with ones to the left. So what does that mean? Well, let's look at these two. We'll follow these rules. We want to see if these are compatible. Well, 1 and 1, these are the rightmost dimension. They're both equal, so it's compatible. 6 and 1, well, one of them is equal to 1, so they're compatible. 1 and 4, these are not equal, but one of them is equal to 1, so they're compatible. And then you have this, but you don't have an element here to the left side. So they don't have the same number of dimensions. Remember, the same number of dimensions is different than not having the same number of elements, which we did above. So if they don't have the same dimensions or the same size, the smaller one gets filled with ones to the left. So this becomes a 1 by 1 by 6 by 1 array. If this were, 2 by 1 by 4 by 1 by 1, then this would become a 1 by 1 by 1 by 6 by 1. So it gets filled with ones to the left so that it becomes compatible with all these dimensions, right? So 1 and 1 are compatible, 6 and 1, 1 and 4 are compatible, 1 and 1, that gets assumed, are compatible, 2 and 1 are compatible. So I would be able to multiply these two arrays together, and it works just fine. Again, if I were to change this to 2, then the 6 and the 2 do not become compatible, and I can no longer multiply these arrays together. And you'll see the benefit of this. You might think, why would you ever want to do this? This is so complicated. Well, I'll show you some cases where this is very useful. So let's look at some examples. Suppose you're tracking the position r of 10 different particles, and you want to multiply the x-coordinate by 2, the y-coordinate by 4, and the z-coordinate by 3. So you have all these different positions of these particles. So your array looks like this, essentially. If I look at r, this is the position of my first particle, second particle, third particle, fourth particle, x, y, z coordinates. I want to multiply all of these by 2, all of these by 4, all of these by 3. And you might be able to do that in a complicated for loop, but using the functionality that I showed above, this is a one-liner in Python. It's very easy to do. So of course, this would be like one particle. And I can look at r.shape. Again, this is good practice. Always, it's a 10 by 3 array. And so what we want to do, we know we want to multiply x, y, and z by 2, 4, 3. So let's create an array. We'll just create an array that is the multiplied values, right? So first dimension by 2, second by 4, by 3. We'll create an array C, like this. C is just the array 2, 4, 3. It's a lowercase c. And if I look at c.shape, it's 3. So we want to see if C and R are compatible in dimensions. Well, let's see, this is 3 and this is 10 by 3. So they don't have the same number of dimensions. So C gets automatically filled with ones to the left. So let's see, well, 3 and 3 are compatible. So we're good. C gets assumed 1 on the left-hand side. 10 and 1 are compatible because one of them is 1. So I'm able to multiply these two arrays together, right? And you might think, well, what's the output going to look like? Well, I can show you. If I multiply C times R, you can see that, and if I compare this to just R on its own, you can see that all of these on the left column have been multiplied by 2. All of these have been multiplied by 4. All of these have been multiplied by 3. So that's how the broadcasting works. That's one example of a useful application for this. And you'll come along these examples sometimes, and it's hard to know beforehand when to do this. That's the point of this video, is to show you, look, here's some examples where this is very useful. We can also apply an operation to a particular dimension of a NumPy array. So operations, of course, include summing numbers together, taking the standard deviation. That's where you take an array, right? Arbitrary number of values, and it returns a number. So it's a function that takes an array, returns a number. One of those functions is a sum. One of those functions is a standard deviation. So here's an array x. I can sum it together, and I get a particular number. So you have a reduce function that says, give me an array, and I'll give you a number back. That's what's happening here. And so you could think, if you have a 2D array which consists of a number of different arrays, and you want to apply that reduction operation, for example, sum all the rows in an array and get an array back, that's an example of operating on the dimension of array. You're operating on the row dimension, and converting all those rows, which are themselves arrays, to numbers. So for example, you can apply the reduction operations along certain axes. So for example, here's an array X that's shape 3 by 10. You can see 10 elements on the first row, 10 elements on the second row, 10 elements on the third row. And maybe you want to take the standard deviation of each row. Maybe each of the 3 rows is a certain person. So this is person 1, person 2, and person 3. And each of the 10 measurements are reaction time. So there's 10 reaction times for person 1 that you measure, 10 for person 2, 10 for person 3. And you want to find the standard deviation of each person's reaction time. Well, you want to take the standard deviation of each of these rows separately. And if I just call standard deviation on the whole array X, it gives me a single number, which is no good because I want it separately for each of the people. Well, I know that the shape of X is, if I call X.shape, it's 3 by 10. So I want the standard deviation of these 10 measurements, right? That's the dimension that I'm taking the standard deviation over. So I'll call a standard deviation on X, but I'm going to specify that the axis I want, axis equals 1, of course, means the second axis. That's the confusing part about indexing, obviously, but axis equals 1, or in this case, axis equals -1, which is the last axis here. It will take the standard deviation over each of these 10 values because this is the last axis, which you can tell using the shape function. This is why shape is so useful. So I have my shape. I want to take the standard deviation of the 10 elements in each of those rows. I call it on the last axis because this is the last axis in the shape, and I'll get the standard deviation of each person. A more complicated example, I have a 2D color image. It's got dimensions height times width times color channel. So height and width are the height and width of the image, maybe 256 by 256. Color channel is the number of color channels in the image, red, green, and blue. That might be 3. So the color channel dimension has 3 elements in it. Height and width dimension have 256 elements in it. So here's a sample image, for example, X, it's 256 by 256 by 3. And again, plot.imshow, because this is the proper dimensions of an image, right? If I load an image in Python, it's going to have these dimensions, especially a color image. I can plot.imshow this. Well, this is just random, so it's just random colors here. But you can see that this is the dimensions of an image, and I can show it like an image. And suppose we want to find the standard deviation between each of the 3 color channels. We want to see how different it is in red, green, and blue for each color channel. Well, let's look at X.shape. Of course, that's always what we want to do. And we want to find the standard deviation between the 3 color channels. I know this is the last axis that I want to find the standard deviation over because I'm looking at the deviation between the 3 color channels for each pixel. And so I call np.standarddeviation X. I take the last axis, that's axis equals 2 in this case, and I get my result. And the result, because I'm doing this for each pixel, it's going to be 256 by 256. So I have a separate standard deviation for each pixel. That's the deviation between the red, green, and blue pixel values. So I'll finish this video with some examples. These are going to combine all the concepts we've learned and useful cases that you might see in research. So here's example 1, and I'll read through this and it'll make sense once we see the array. Suppose you're studying 3 rats, rat 1, rat 2, rat 3. Those rats are in a cage. And there's 20 different feeding containers in this cage. And you wait a day and you count the number of times that each rat feeds out of each container. And you want the probability that a given rat is going to feed out of a given container. So each rat maybe has different feeding preferences. They'll have a different probability of choosing a container to eat out of. So for example, here's my array. So here's rat 1. He eats out of container 1 2 times, container 2 0 times, container 3 6 times, and so on and so forth. Here's rat 2, how many times he ate out of each of the 20 containers, and rat 3. We want to find probabilities. So right now these are numbers, and we want to convert these. We want to normalize each of these axes, right? So again, let's look at X.shape. It's 3 by 20. So we need to normalize by the number of entries in each, or the sum of these, right? So if I divide this by the sum, it will give me probabilities. So if I want the sum along the 20, right? So that's the it's the second axis, but index 1. So I can call x.sum axis equals 1. This tells me how many times each of these 3 rats fed in total, right? So this guy fed 50 times of all the different 20 containers. This guy fed 64 times. This guy fed 62 times. And what I want to do is I want to normalize each of these so I get probability. So I want to divide this by this number, this by this number, and this by this number. So we need to divide. So again, this is our, I'm going to call this total equals this. And let's look at the shape of total. Well, total has a shape of 3, but x has a shape of 3 by 20. So if I try to multiply or divide basically this array, x, by total, it's not going to work because 20 and 3 are incompatible. But what I can do is I can reshape total so that it can be divided. And the way I can reshape it is using the functionality before, dot reshape. So what I'm going to do is I'm going to give the first dimension a shape of 3 and the second dimension a shape of 1. So then 20 and 1 are compatible and 3 and 3 are compatible. And my array now looks like a column vector as opposed to a normal row vector. So this is my total.reshape 3, 1. So this is how I would normalize the array. If I divide x, right, like this, by total.reshape 3, 1, which looks like this, it will divide this by 50, thus giving me probabilities, this by 64, giving me probabilities, and this by 62. The reason I know that is because I look at the shape of each of these. This total.reshape 3, 1 is the shape of 3, 1. This is 3 by 20, and these two arrays are compatible for operations. So then it's very simple. I just do result equals x divided by total because these two arrays are compatible for operations. I can get my result. And the reason for that error is because I forgot to say that total equals, so we're going to change the shape of total like this. So total equals total.reshape 3, 1. Now if I look at the shape of total, it's a shape of 3 by 1. This is a shape of 3 by 20. These are compatible for operations. I do result equals x divided by total, and I can plot the probabilities on a plot, right? Because if I look at my result, it's now a 3 by 20 array. This is the probabilities corresponding for the first guy, the probabilities for the second guy of each of the 20 containers, the probabilities of the third guy. So I can plot them. I'm just going to plot the probabilities of the first guy. So if I index result 0, this gives me the probabilities of the first guy eating out of all the different cages. This is just a little bit of matplotlib. And you can see that now I have the probabilities in percent. By the way, I multiplied this by 100 to get percentage. And these are the probabilities of the first rat eating out of all the different containers. Then I can plot the second rat and the third rat. The main thing is that this can be put into a very simple operation. And in fact, if I was doing this, if I just had x, I would just go like this. This is how I would chain it all together. X divided by x dot sum, x equals 1. That's not a compatible shape though, so I'll reshape it to 3 by 1. So it's a single line to normalize this array as follows. And I get my result. I can plot the result and we're good. So here's another really good example. This shows up a lot, by the way. Not this particular circumstance. It probably never shows up, but the functionality we'll use here shows up so much. I don't know why I thought of this example. So you have an array containing the blood pressure of a turtle every 6 hours. You take 4 measurements per day. By the way, this is done with humans all the time. If someone has a blood pressure monitor, they put it on 24 hours, you take a bunch of measurements. So for example, this turtle has that. He's taking 4 measurements per day. And you take 100 total measurements. So 25 days, 4 measurements per day, 100 total measurements. You want to compute the mean blood pressure of the turtle each day. And maybe you also want the standard deviation throughout the day as well. How much does, in a given day, how much does the blood pressure vary? Well, don't worry about this. This is my data. So here's my blood pressure every day of this turtle, right? And I want the mean, and I'm also going to find the standard deviation as well. So I know that these 4 measurements correspond to the first day, these correspond to the second day, next day, so on and so forth. So how do I get the mean of like 4 consecutive elements, the mean of these 4 elements, etc.? Well, what I can do is I can reshape this array. So if I call x.reshape, by the way, I'll start like this. If I reshape it to a 25 by 4 array, it tells me that now I have 25 arrays, right? Each of those array has 4 elements total. So these are the first 4 elements. Those are the first 4 blood pressure readings, the second 4, the third 4. So I'm reshaping it so the last dimension right here is the number of readings per day. By the way, if I knew that this was divisible by 4, maybe I didn't know it was 100. If I add a -1 here, it's automatically going to take 100, because that's the size of the array, divided by 4 and fill that in here. So -1 is a placeholder that allows you to do the same thing. If, for example, maybe you don't know how many measurements you took total, but you know that it's divisible by 4. If it's divisible by 4, then this will work. NumPy will automatically know what number to put here. So I reshape it as follows. That's the first thing I do. And so I have my shape. It's 25 by 4, and I want to take the mean value along the last dimension. So what I do, exactly the same as before. I take the mean value, dot mean, and I do it along axis equals -1. So it'll take the mean of these 4 elements for each of those different arrays. And then I get 25 total measurements corresponding to the mean each day. I do the same thing with the standard deviation. So these are my results, x.reshape -1, 4. Then I take the mean along the last axis. So it takes the mean of those 4 elements. Same with the standard deviation, and I can plot them. And you can see that these are the mean values of the turtle each day. It's kind of slightly going up. And then the standard deviation sort of gives you an estimate of the variation of those measurements. So this was the mean value. This was sort of the variance of the measurements. And it can sort of look like this. So this will show up a lot in research where you need to sort of, you have a time series and you want to take averages of like consecutive portions. That's a huge example all the time that shows up. And rather than creating a complicated for loop and filling an array, using this functionality allows you essentially to do it in a single line. Final example, really short. You have 4 256 by 256 images, which have 3 color channels each. And you want to set the green color channel of all images to the green color channel of the first image. I don't know why you want to do that, but maybe you want to do that. So here's your array. And again, always good. Look at the shape. So 4 images, 3 color channels, 256 by 256. Well, I want to get the color channel of the first image. In order to do that, I use indexing. So the first image is index 0. That's my first image. The green color channel is index 2. So this gives me the green colors of all the pixels in this array. And again, I can look at the shape. So it's 256 by 256. It tells me the green color channel and all the pixels of the first image. And I want to set the green color channel of all the images to this image. Well, I can index like this, right? Here's x dot shape. So now it gives me 4 by 256 by 256. This is the green color channel of all 4 images, 256 by 256, because I'm just grabbing that green color channel. X02, this is the green color channel of the first image. It's 256 by 256. And I want to set this right here equal to this. And I want to know if these are compatible for operations. Well, they are. This is sort of the grand finale of all this, right? This is 256 by 256, and I compare dimensions. Well, 256 and 256 are compatible. 256 and 256 are compatible. And then, of course, this is missing one. This is longer, so this automatically gets filled with a 1. 4 and 1 are compatible because one of them is equal to 1. So I can do this operation safely in NumPy. And I set the green color channel of all the images equal to the green color channel of the first image. I hope you enjoyed this video. I hope it's useful for your research later on. I hope it saves you writing a lot of for loops. If you enjoyed this video, please be sure to like and subscribe, and I'll see you next time.